Hey everyone. So in this video, I want to talk about another formula that allows us to calculate the future value of an investment or a loan, taking a look at the interest when it's compounded. In this case, our interest is going to be compounded continuously. We've already looked at the formula for compound interest when we're compounding a certain number of times a year. So that involved the variable n, where n was the number of times our interest is compounded. So for example, if we're compounding monthly, n would be 12. But now I want to think about, what if I compounded it continuously? In other words, what if that variable n could increase without bound? What would happen to our formula? So just to remind ourselves, the formula for compound interest looked like this. Our future value was equal to our principal times 1 plus r over n raised to the nt power. So the variable n in this formula, that represents the number of times it's compounded. As I said, if we're compounding monthly, n would be 12. Another case would be maybe I'm compounding daily, then n would be 365. But now what happens if n gets very, very large, right? What if I'm compounding my interest hourly, or by the minute, or by the second, or I keep increasing the number of times I'm compounding? So I can't just plug in infinity into this equation. Infinity is not a number. I won't be able to calculate anything. But what I am able to do, with a little bit of algebra, I can actually isolate the term 1 plus 1 over n raised to the n power. So I'm isolating anything that has the variable n in it. And we have this concept in math called limits. So what I want to do is I want to think about, what is the limit of this expression as n approaches infinity? So what's going to happen to this expression as n gets very, very large? And what it turns out is this expression actually approaches the number e. So e is an irrational number, which is about 2.71. A rational number, it continues on forever. It's a non-repeating, non-terminating decimal. So if this expression approaches the number e, I can adjust my formula, and what we end up with is the future value is equal to our principal times e, the number e, raised to the rt power. And this is the formula we want to use to calculate continuously compounded interest. So why don't we use this in a couple examples? So the first example says you decide to invest $4,000 for 5 years into an account that pays 3.5% interest, continuously compounded. The first thing, whenever I see this phrase, compounded continuously, I know that I want to use my formula. A is equal to P times E to the RT power. How much money will be in the account after 5 years, and how much interest was earned? So our principal investment, the amount of money we're putting in, is $4,000, so we'll plug that in for P. We have E, and then we're raising this to the RT power. So R is my rate, written as a decimal, so that is 0.035. And then we're going to have this in here for 5 years. So then we'll multiply that by 5. I like to do a little bit of simplifying first. So we end up with 4,000 times E, and then in my exponent, 0.035 times 5, I end up with an exponent of 0.175. And now from here, I would want to type this into my calculator. So when I type it in, I just need to make sure to follow order of operations. So I'm going to do my exponent first, and then I'm going to multiply that by 4,000. So taking a look, we have our button for e raised to a power, and we want to raise this to the 0.175 power. So that's taking care of the exponent. And then we're going to multiply this by 4,000. So what we end up with is we get about $4,764.98. So that will be our future value. That's how much in the account after the 5 years. If I want to calculate the interest, we just need to take our future value and subtract our initial investment, our principal. So we'll take the $4,764.98. We'll subtract our initial investment of $4,000. So the interest that we earned was about $764.98. All right, let's take a look at one more example. In the second example, I actually want to do a comparison. So it says you decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first account pays 7% per year, compounded monthly. Okay, so the first thing right away, compounded monthly, since n is going to be 12, I know I need to use this formula. So P times 1 plus R over N to the NT power. The second investment pays 6.9% per year, but this one is compounded continuously. So there's that phrase again, compounded continuously. I know I need to use A is equal to P times e to the RT power. So if n is finite, if n is a certain number, I want to use this first formula. If I'm compounding continuously, we're going to use our new formula. So let's plug in what we know. So our principal is 8,000. For this first one, we have a rate of 7% per year, so that's 0.07. N is going to be 12 because we are compounding monthly. And then in the exponent, we're going to have n is 12, and our time is going to be 6 years. In our second equation, we have the same principal of $8,000, and then e raised to the power, our rate, 6.9%, that's the same as 0.069, and then we'll multiply that by the time, which is 6 years again. Okay, so now that we plugged in all the information we know into our equations, let's use our calculator to find out what the future value is for both of these. So to show you how to do this, I want to work my way from the inside out. Again, I'm just following order of operations. So for the first one, we have our rate divided by 12. So that's our fraction. And then to that, we're going to add 1. And I'm going to hit enter again. So we have 1.00583 repeating. And then we want to raise that to the 12 times 6 power. So in parentheses, I will type 12 times 6, which is 72. So that gives me 1.52-ish. And then the last step is we're going to multiply this by 8,000. So multiplying by 8,000, we end up with a future value of 12,160 and about 84 cents. So I'll write that down here quick. So we have about $12,160.84. And now let's go through that for our second expression as well. So we have our exponent, so we'll take care of that first. So our rate of 0.069, multiply that by the years, which is 6. So our exponent is 0.414. So we want to take e and raise that to the 0.414 power. So this is what I end up with after calculating the exponent. And then the last step is we will multiply by 8,000. So multiplying by 8,000, we end up with a future value of $12,102 and about 86 cents. So we end up with about $12,102 and about 86 cents. And now comparing these two investments, which one is going to give us a greater future value? It's actually going to be the first one by roughly $58. So the better investment is going to be the one that's compounded monthly. So a good thing to think about with this is that the number of times we compound doesn't necessarily mean it's the better value. In a lot of cases, it's actually the rate which is going to make the biggest difference. So because that first account has a better interest rate, we actually do end up with a better future value.